Hi, I'm Swarupa Sail, course instructor for Fluid Mechanics. In this presentation, we will go through Euler's equation of motion. Euler's equation of motion of an ideal fluid for a steady flow along a streamline is a relation between velocity, pressure, and density of a moving fluid. Euler's equation of motion is based on the basic concept of Newton's second law of motion. When fluid will be in motion, there will be some forces, and those forces which have to be considered are pressure force, which is represented as Fp, gravity force Fg, friction force due to viscosity, that is Fv, force due to turbulence, that is Ft, and force due to compressibility, that is Fe. So the total force Fi is summation of Fp, Fg, Fv, Ft and Fe. Here the forces due to pressure and gravity are predominant, hence other forces are neglected. So Fi is equal to Fp plus Fg. Some of the assumptions made are, first one is the fluid is non-viscous and frictional losses are considered to be equal to 0. The fluid is homogeneous and incompressible. The flow of fluid is steady, continuous and along the streamline. Fluid flow velocity is uniform over the section, and only gravity force and pressure force are taken into consideration. So here, hence it is Fi is equal to Fp plus Fg. So these are the some of the assumptions which are made in Euler's equation of motion. Now consider fluid flowing from point A to point B through a cylindrical section of length ds. Let the cross-sectional area of this cylindrical section be dA. Now let us consider the forces acting along this cylindrical element. So first one is the pressure force, that is P into dA, which is acting along the direction of fluid flow. And the other force is the pressure force, which is P plus increase in pressure along length ds, that is dou P by dou S, and this increase in pressure is along the length ds. So here it is written as ds, and this pressure force is acting along the cross-sectional area dA, and this is acting in the opposite direction of fluid flow. So here PdA is acting along, let us say, along the direction of S, whereas the pressure force, that is P plus dou P by dou S into ds into dA, is acting opposite to P into dA. Now let us consider the weight of the fluid element, which will be equal to mass into acceleration due to gravity. So it is W is equal to m into g. And if we write m in terms of density, we know that density is equal to mass by volume. So m can be written as density rho into volume into g. So rho will be written as it is, and volume of this cylindrical section is dA into ds. And acceleration due to gravity is written as it is. So the total value of W becomes rho g dA into ds. Let the angle theta be the angle between the direction of the flow of fluid and the line of action of weight of the fluid element. And we know that the Euler's equation of motion is based on Newton's second law of motion. So net force over the fluid element in the direction of S is equal to mass of fluid element into acceleration in the direction of S. So we write F is equal to m into A. And already we have seen the equation, that is Fi is equal to Fg plus Fp. So first we will write pressure force, that is P dA minus P plus dou P by dou S into ds into dA, and force due to gravity can be written as rho g dA ds cos theta. We know that W is equal to rho g dA ds, and this is acting at an angle theta from direction, that is S. So the component of this weight along S direction will be rho g dA ds into cos theta. So that is what is the gravitational force, that is rho g dA ds cos theta. And this is equal to inertia force, that is mass into acceleration. Mass is density into volume, so it is rho dA ds into as, that is acceleration, and this is the acceleration in the direction of S. So it is written as as. As can also be written as change in velocity with respect to time. So it is dv by dt, which is equal to dou v by dou s into ds by dt plus dou v by dou t, which is equal to v into dou v by dou s plus dou v by dou t. If the flow in this cylindrical section is steady, then dou v by dou t is equal to 0, because variation of the parameters with respect to time is equal to 0 in case of steady flow. So we write the same equation as dou p by dou s into ds dA minus rho g dA ds cos theta equal to rho dA ds into v dou v by dou s. Here dou v by dou t is substituted as 0. Now divide this equation by rho dA ds. Now we get minus dou p by rho ds minus g cos theta equal to v dou v by dou s. So the same equation is dou p by rho ds plus g cos theta plus v into dou v by dou s equal to 0. Now from this figure we can see that cos theta is equal to dz by ds. So we will substitute the value of cos theta in this equation, and we get 1 by rho into dou p by dou s plus g into dz by ds plus v dou v by dou s equal to 0. And the same equation can be rewritten as dou p by rho plus g into dz plus v into dv, which is equal to 0. Thank you.